You ever ask a chatbot the same question twice, maybe just minutes apart, and get a slightly different answer? It's weird, right? But what if I told you that happens even when you tell the AI, hey, be perfectly consistent, no creativity? Well, that's what we're diving into today. We're going to solve the very strange, very fascinating puzzle of why our most advanced AIs just can't seem to give us the same answer twice.
I mean, it's a pretty basic question, isn't it? If you lock down all the settings, if you take away all the randomness, you should get the exact same output every single time. But with these huge language models, that's just not what happens. So the real mystery we're tackling is, where is this unpredictability, this non-determinism, actually coming from?
So get this. Researchers prompted a model about Richard Feynman, not once, but 1,000 times. And they set what's called the temperature to 0, which basically means it's supposed to always pick the most obvious next word. And for 102 words, it worked perfectly. Every single response was identical. But then, on word 103, some answers said Queens, New York, while others said New York City. Now that might seem like a tiny difference, but scientifically, that's a huge deal. It's a crack in the foundation. This just shouldn't happen.
All right, so to solve any good mystery, you have to start with the usual suspect. This is the explanation you'll hear most often. It's the one that sounds super smart and plausible, the one that gets passed around on forums and in papers. But as we're about to find out, it doesn't quite tell the whole story.
And here it is, the official story. Let's call it the concurrency plus floating point hypothesis. The big idea is that the way GPUs do math, running a gazillion calculations all at the same time, creates these tiny, unpredictable errors. And those errors snowball into different final answers. It sounds really technical, it sounds right, but is it the whole truth? Okay, so to understand the suspect's motive, we need to talk about something called non-associativity. You know how in school you learned that it doesn't matter what order you add numbers in? Well, for computers dealing with decimals, what we call floating point numbers, that's not true. The order matters a lot. It's this fundamental quirk, kind of like the original sin of how computers do math.
And check out how big a difference this can make. It's kind of shocking. If a computer adds a tiny number, like 0.1, to a gigantic number first, it just doesn't have enough precision. The tiny number gets rounded away, it vanishes, it's just 0. But if it deals with the two giant numbers first, they cancel each other out perfectly and the tiny number survives. We're using the exact same numbers, the exact same operations, and getting completely different results. That is the heart of the problem.
So this brings us back to that popular theory. You've got a GPU, which is like thousands of little calculators all working at once. The theory goes that we just don't know which little calculator is going to finish its job first. This random finishing order shuffles the order of addition. And because of those floating point quirks we just saw, that shuffle leads to a different final answer every single time. Makes sense. Case closed, right? Well, not quite.
And here comes the plot twist. If that whole theory were true, if it were the whole story, then any simple parallel calculation on a GPU should also be a little bit random. But what happens when you actually test that? Well, the researchers found something that kind of blows the whole case wide open.
They ran a totally standard matrix multiplication on a GPU 1,000 times. Now this operation has all the ingredients for randomness. It uses floating point math, it's massively concurrent, and the result? Every single time, the output was bitwise identical. Perfect copies. Absolutely predictable. This is the alibi for our usual suspect. It proves that the concurrency plus floating point story is just not the full picture. Something else is going on.
So if it's not some random race between the tiny calculators inside the GPU, what in the world is it? Well, the investigation uncovered the real culprit, and it's actually something way more subtle, something that has everything to do with making these models run efficiently. The real problem is a lack of something called batch invariance. Let me give you an analogy. The route your Amazon package takes to get to your house shouldn't change just because the delivery van is full of other people's packages, right? Your results should be independent of everyone else's. But with LLMs, it's not. The actual math for your question literally changes depending on how many other people are asking questions at that exact same moment.
And folks, this is the smoking gun. In that first line of code, we do a calculation on just one single item. In the second line, we do the calculation on a huge batch of items, and then we just pull out the result for that exact same single item. Logically, mathematically, these should be identical. But look at the difference. It's over 1,600. This is not some tiny little rounding error. This is a fundamentally different outcome, and the only thing that changed was the batch size. So here's how it really happens. The number of people hitting the server at any given second is completely random. To be efficient, the server bundles all our requests together into these batches of different sizes. That changing batch size, as we just saw with that smoking gun, actually alters the math for your specific request. And there you have it. That's why you get a different answer than you did 5 minutes ago. Mystery solved!
So now that we've unmasked the real culprit, the next question is obvious. Can we fix it? Can we actually force these models to be consistent without, grinding them to a halt? Well, the answer, thanks to some really brilliant engineering, is yes. Let's take a look at how they pulled it off.
The solution was basically a surgical strike. The researchers went in and identified the 3 specific parts of the model's architecture that were causing the problem, the ones that were not batch invariant. Then, they carefully rewrote the code for just those operations to guarantee that the mathematical journey your quest takes is identical, whether it's flying solo or packed in a batch of 1,000. Now, this was not a simple fix. It meant changing the fundamental way calculations were combined for things like RMSNorm, matrix multiplication, and the really important one, the attention mechanism. They had to force the order of operations to be fixed, even when the normal code would try to change it on the fly to be more efficient.
Of course, the million-dollar question is always performance. Is there a price for this kind of precision? And yeah, there is. The first deterministic version was about twice as slow, but with some more clever optimizations, they managed to close that gap quite a bit. It's a real trade-off, for sure, but the performance is definitely still in a very usable range.
Okay, so you might be sitting there thinking, this is kind of cool for nerds, but do I really care if my chatbot response is exactly the same every time? And that's a fair question. The thing is, the real payoff here isn't about chatbots at all. It's about unlocking the entire next level of AI research. See, the really crucial thing this enables is a technique called true on-policy reinforcement learning. That's a super powerful way for an AI to learn, by basically doing experiments and seeing what happens. But that can only work if the world it's experimenting in is predictable. If the model does the same thing twice and gets 2 different results, it's like trying to learn physics in a world where gravity just randomly changes. It's totally impossible.
And you can literally see the impact right here. This chart shows something called KL divergence. You can just think of it as a measurement of the gap between what the model thinks is going to happen and what actually happens. Without determinism, that gap is huge and all over the place. The model can't learn. But with this new deterministic model, that gap completely vanishes. 0. A KL divergence of 0. That means the model's predictions and its results are in perfect alignment. It can now learn reliably from its own experience. A massive roadblock for training more advanced AI has just been completely removed.
So, we've gone on this pretty deep dive, all the way into the guts of GPU math and AI servers. So what's the big takeaway here? What's the one thing we should really remember from all this?
I think this quote from the researchers who did the work just says it all. It's so easy to look at these giant, complex AI systems and just shrug and accept their weird quirks. To just say, it's a black box, who knows? But this work is a powerful argument against that kind of thinking. It shows that if we're rigorous, if we're persistent, we can understand and we can control these systems on a really deep level.
And that really leaves us with one last thought. We just saw how solving this one, seemingly small problem of consistency actually unlocked a whole new way to train AI. It just makes you wonder, right? What other breakthroughs are just sitting there waiting for us if we simply refuse to accept good enough and instead demand real, true precision from the incredible tools that we're building? What new possibilities are we going to unlock next?